page 24, section 1.2 is mathematical models. Mathematical models. They tell me that a mathematical model is a mathematical description, often by means of a function or an equation, of a real-world phenomena such as the size of a population, the demand for a product, the speed of a falling object, the concentration of a product in a chemical reaction. I mean, it just goes on and on and on with all kinds of real-world situations where, let's take that first one that they talked about there, the population. We could go through and we could collect all of the census information for the city of Savannah from the past 20 years. And we could take that data and we could make a table of values from it. We could graph that. From that, we could figure out, is it linear? Is it exponential? Is it logarithmic? Is it, what type of a model is it? And then we could use our calculator to do a regression to try to fit an equation to that model of information. Then from there, we could use that as a predictor of, okay, what's the population going to be 10 years from now, so we know how to prepare in terms of a job market and housing and transportation and that type of thing. They may not have taken a census every year during that 20-year time span, and we have an interest in a particular year where they didn't take census information. If I have that equation, then I could go back and plug in that missing year and get an approximation of what the population may have been during that time. So that's the idea of a mathematical model. So over on page 25, they give us a diagram of the modeling process. And it says, Figure 1 illustrates the process of mathematical modeling. Given a real-world problem, our first task is to formulate a mathematical model by identifying and naming the independent and dependent variables. Now, we've talked about that a little bit already, that when we're working in calculus, typically we associate domain with X and range with Y. But in that scenario we were just talking about with population, I don't have an X and a Y. I have a P for population and a T for time or something like that. I'm not going to have an X and a Y. So I'm going to have to think about, does the population depend on what year it is, or does what year it is depend on the population? And of course, I don't get to set time. I don't get to set the calendar. I don't get to determine what year it is. So the population is going to depend on the time. So that makes population my dependent variable, my range value, if you want to think of it that way, and that makes the year my independent variable, or my X value, or my domain, if you want to think of it that way. So once we figured out the independent and the dependent variables, it says that in some situations where there is no physical law to guide us, we may need to collect data. Now, sometimes I have a physical law. Let's say that we're talking about the distance that marathoners went for the rock and roll marathon. And we're talking about their times, and we're calculating their rates and that type of thing. I have a mathematical formula for that. Distance equals rate times time. I don't have to reinvent the wheel. But in a situation where there's no physical law to guide us, then we may need to collect data, examine that data in the form of a table in order to discern patterns. So I could look at that data and then I could decide, is it linear? Is it exponential? Is it cubic? Is it, what type of a thing am I working with? And it says, the graph might even suggest a suitable algebraic formula that we could use in some cases. Right? Then the second stage is apply that mathematics that we know to derive mathematical conclusions. We could take those mathematical conclusions and interpret them as information about the original real-world phenomenon. Like we were mentioning, we could use it to fill in for years when the census wasn't taken, or to use it as a predictor for what might happen down the road. That's what we're talking about, applying the mathematics that we know to that equation that we generate, or that graph that we generate, or that table that we create. Now, one thing they mention is that a mathematical model is never a completely accurate representation of a physical situation. It is an idealization. So, okay, I collect all this census data for the past 20 years, and I plot it, and I graph it, and I do a regression, and I create an equation that fits that information, and I use it to predict what the population in Savannah is going to be 10 years from now. Does that mean that that's exactly what the population in Savannah will be 10 years from now? Of course not. There's a million things that could happen between now and then that could affect that number. It's just an idealization. In an ideal world, in a perfect situation, in a perfect scenario, this is what we would have, but this is the real world. So there are going to be other factors that would affect it. So a mathematical model is never a completely accurate representation of the physical situation. All right, so the first thing they talked to me about on the bottom of 25 is a linear model. Now, we've already worked extensively with linear equations in the appendices, but again, they're assuming we didn't do that, so they go back through y equals mx plus b and how to graph a line and that type of thing there. So we're going to go straight to example 1. Example 1 says, as dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of the height h in kilometers, assuming that a linear model is appropriate. So they were kind to give us a really big jump start here that this is a linear model. Okay, so step number 1, remember they had told us on the previous page, your first task is to identify and name the independent and the dependent variables. Because again, I don't have an x and a y here. I have a temperature and a height. I have a t and an h. Okay, so does the temperature depend on the height I am off the ground, or does the height I am off the ground depend on the temperature? The temperature depends on how far off of the ground I am, right? So if the temperature depends on, that means the temperature is the dependent and the height is the independent. So we'll put height where we normally put x and we'll put temperature where we normally put y. So in our ordered pair, it's going to be ht. We could say that t is a function of h, just like we would normally say y is a function of x. So we're going to write an equation for temperature in terms of the height. Right? So first off, let's collect some information here. It says the ground temperature is 20 degrees Celsius. What's the height of the ground temperature? 0, right? If you're on the ground, your height is 0, right? So that would give us an ordered pair. We could say when my height is 0, my temperature is 20 degrees. Then they also said that the temperature at a height of 1 kilometer is 10 degrees Celsius. All right, so you could write that as another ordered pair if you want to. You could write that as 110. So then I would have 2 points, and I could use my slope formula, right? So I could go through and I could say y2 minus y1 over x2 minus x1, which of course would just be 1 minus 0 in my denominator. So that would be a slope of negative 10. You could have also just used common sense and said, okay, every time I go up 1 kilometer, my temperature drops 10 degrees. So that means that my slope is negative 10. So it asked us to express that temperature as a function of the height, assuming that a linear model was appropriate. So if this is linear, I can use y equals mx plus b. So what's m? Negative 10. What's b? 20, right, because b is our y-intercept, right? And we get the y-intercept when x is equal to 0. So we could go through then and say y equals mx plus b. T is equal to negative 10h plus 20. For b, it says draw the graph of the function. So we absolutely could graph that. Y-intercept at 20, slope of negative 10. So rise negative 10, run positive 1. You can see that graph there in your textbook in figure 3 on the bottom page 26. What does the slope represent in that problem? That negative 10, what does that slope represent? What does the slope represent, that negative 10? Okay, so it represents the change in temperature as I go up in height. If you think about your slope formula, it's usually the change in one quantity divided by the change in another, right? We're going to express that as a rate of change. So we're going to say it's the rate of change of the numerator over the rate of change of the denominator. So in our case, it would be the rate of change of the temperature in terms of the height, or the rate of change of the temperature with respect to the height, or something along those lines. But in calculus, we spend a lot of time working with rate of change. So it's going to be the rate of change of the numerator in terms of the denominator. So rate of change of the temperature in terms of the time, or with respect to the time. All right, then for C, it says what's the temperature at a height of 2.5 kilometers. So how could I find that? Okay, put 2.5 in for H. So if I plug 2.5 in for H, I get a negative 5 degrees Celsius. Does that mean that if I hold a temperature probe 2 feet off the ground, that it's automatically going to have to be negative 5 degrees Celsius? No, it might be negative 4.8, or it might be negative 5.1, or a gust of wind might come by and it might drop to negative 6. You know, it's a mathematical model, so it's just an idealization. On the bottom of page 26, they tell me if there's no physical law or principle to help us formulate a model, then we're going to construct an empirical model, which is based entirely on collected data. So, if I don't have any kind of a law about the population in Savannah, I'm going to need to go through and pull the census records for the past however many years that I want, and use that data to help me construct an empirical model. Your empirical model is only as good as your data is, and so it's extremely important for you to look at the source of your data. If you are trying to make a farmer's almanac that's going to predict the tides for the next, however many years, and you're going to publish this, you need to make sure that your data is accurate. It's not just somebody going down to the river, for the past year. It was my next door neighbor who happened to have, the river running through his backyard, and he went and took his own river readings every day, and I'm basing my almanac on that? No, of course not. They're going to be very scientific readings. They're going to be checked multiple times over at multiple places and multiple stages, and your model is only as good as your data. You need to look at the source of your data as well, in terms of, do they have any bias? If the source of your data is an advertising company that's trying to sell a particular product, they may go through and collect a whole bunch of information, but they may only report the information that is beneficial to them in their product. So yes, they're reporting the correct numbers, but they're only reporting the things that lead the data in the direction they wanted it to go anyway. So it's extremely important that we have accurate numbers to work with. Our model is only going to be as accurate as the information that we start with. So example 2 says, table 1 lists the average carbon dioxide level in the atmosphere measured in parts per million at the Mauna Loa Observatory from 1972 to 1990. Use that data in table 1 to find a model for the carbon dioxide level. Okay, so if we went through and we took all of the information in table number 1 and we plotted it, you would get that graph that you see there in figure 4 on the top of page 27. What does that look like to you? Does it look linear, quadratic, exponential, logarithmic, cubic? What does it look like? Yeah, it looks linear to me. Doesn't have to be linear. Some of the information they give us could definitely be something else, because we have all kinds of regression capabilities on our calculator, but that does look linear. So I don't have a law already in existence that tells me what those numbers are going to be. So I'm going to create one from the information that I have. So I'm going to create a linear equation. To create a linear equation, I only need 2 points, right? So I'm going to choose the first point, 1972, and I'm going to choose the last point, 1990, because I want to make sure that I get like the full spectrum of the timetable that we're looking at. So if I have those 2 points, I could go through and do y2 minus y1 over x2 minus x1 to find my slope. And then I could use either one of those points. I chose the first one. And use my point slope form, y minus y1 is equal to m times x minus x1, and simplify that. And that would be my equation of what I think is a model of that information that was given. Now, what's wrong with that equation? It is only based on those 2 points. So I basically told these people that they wasted all their time and money for all the other years that they collected the information. Anything else? What if one of those years the reading was not typical for that observatory? Maybe there was human error, or maybe it was just a off year, and it would not be indicative of what would be true the rest of the time. I really can't just go on 2 points. I really would need to go back, and I would need to calculate the slope between 72 and 74, and between 72 and 76, and between 72 and 80, and 72 and 78, and 72 and 82, and 72 and 80. I mean, the whole way down the chart, right? And then I'd have to go back and look at 1974 and say, okay, I already did 72 and 74, but I haven't done 74 with any of the rest of these. So then I'd have to do 74 with all the rest of them. And then I'd have to do 76 with all the ones down below it, and 78. We could be here all day, right? I mean, we could sit here and do fundamental counting principle to figure out how many slopes I'm actually going to have to calculate, and then average all of those together to try and get the best estimate of what the slope really should be. And then I'd have to go back and do the same thing with the points, and then create these equations. And it's just crazy. There's no way I can do that on multiple situations and multiple problems. That's where my calculator can help me. Because remember that my calculator does something called a least squares regression, where it'll go through and it will analyze all that information and create the equation for me. So let's utilize our calculator to help us with that. So grab your calculator if you would. All right, so let's go through and let's put the information in list 1 and list 2. So you're going to go to statistics, and you're going to go to edit. It's a good practice to clear out your list before you begin. So you would go up to list 1 and hit clear and then enter, and it would clear everything you have in that list. Why is that important? Because this list extends down below what I can see. Like if you'll notice, the last entry here is 1984, but the table actually goes all the way down to 1990. So tomorrow when I come in to take my quiz, if I come in and I type on top of these numbers and I forget that there are numbers down below and I didn't clear them out, all of my answers are going to be wrong, right? So it's just good practice. Scroll up to list 1, hit clear, enter, and it'll clear that whole list, and then you can just start typing in fresh. Same thing with list 2. Do not hit clear, delete. If you hit clear, delete, you literally will delete that list. Is there anybody that's missing any of their lists, like 1, 2, 3, 4? Okay, easy fix for that. If you go to statistics and go down to number 5, setup editor, hit setup editor and then hit enter, and it'll say done. And now when you go back to edit, you'll have all of your lists. Is it there now? Whoa. There you go. So it's an easy fix if you accidentally hit delete instead of enter. It's not tragic, but hit clear, enter to clear your lists. Now be sure that you double check all of your information once you get it in, because if you type in anything wrong, then it again will cause all of your answers to be wrong. So let me call these out to you and make sure that you have them all entered correctly. So you should have 1972, 327.3, 1974, 330, 1976, 332, 1978, 335.3, 1980, 338.5, 1982, 341, 1984, 344.3, 1986, 347, 1988, 351.3, and 1990, 354. Now, we easily could set our own window by looking at our X values and saying, okay, my X values are going from 1972 to 1990, and my Y values are going from 327 to 354. But rather than having to set the window by hand, remember that when you're working with statistics, you have a Zoom Stat button. It's number 9. So if you hit Zoom 9, it will set the window for you. Let me go turn my Y equals off because I still have something running in here from before. So it set a perfect window for me. And you'll notice that generated a graph that looks identical to the one that we had there in the textbook. Now, we had created an equation by hand using just the first point and the last point. So that equation was y equals 1.48333x minus 2597.83. All right, so that was the equation we created using the first and the last point. So if I put that in, I typed in something wrong. 1.48333. Oh yeah, 2 x's, that'll do it. Okay, that's better. So there's our graph. And you'll notice that it's a pretty good fit. It's not terrible. But my problem is that I only am hitting like the first couple blocks and the last couple blocks. Most of my data is running below that. So that probably means the 2 years that I picked were a kind of high estimate. And I'm not getting a really good read on this information. All right, so we would like to get our calculator to consider more than just those 2 points. We want it to consider all of them. So I'm going to go back to statistics, and this time I'm going to go over to calculate. And because this was linear, I'm going to choose linear regression. Now, you can see I have lots of other options down here. If it had looked like a parabola, I would have done the quadratic regression. If it had looked like the S-shaped, I could have done the cubic. If it looked like the W or the M, I could have done the quartic. I also have a natural logarithmic. I have an exponential, a power. I even have sine regressions down here if it looks more like a trigonometric. So I have all kinds of options. But I'm going to go back up to our linear regression here, which was number 4. Now, when I choose number 4, before you hit enter, if you want your calculator to automatically load that equation for you into y equals, then you need to tell it that. And you can tell it to put it wherever you want. Like right now, I have my approximation in y1. So if I wanted to compare my approximation with the calculator's approximation, then I would probably want to tell it to load it maybe in y2. If that's the case, I just type y2 right here. I actually want the calculator so that you can see it really does replace that equation. I'm going to tell mine to go to y1, and it literally will put the new equation on top of the old one instead of having 2 to compare. But you can tell it whatever you want to here. So with the new operating system, you're going to choose alpha F4. and that's your shortcut menu to get your Y1. If you don't have the new operating system, or if you have a calculator older than an 84, like an 83, then the way that you find that is you go to Variables and go over to Y Variables and choose Function, and that's where you would get your Y1. Okay, so I'm going to tell it, do a linear regression and load it in Y1. So there's the equation. So it's telling me that A should be 1.496 repeating, and B should be negative 2,624.826 repeating, so I could plug those in for A and B if I were typing it in by hand. But you'll notice that if I go to Y equals, it's automatically typed that in for me. So now if I go look at the graph, that's a much better approximation. It's hitting more of the points. I'm getting a better idea. So that's step number 1. Step number 2 that they had told me on those models was then I could apply mathematics to utilize that information. So the way that I would utilize that is in example 3, it says, okay, now use that linear model you just created to estimate the CO2 levels in 1987. They didn't take this data in 1987. It's not in my table, but I can get it now from my graph. So I can do a second trace and choose my value button and just tell it I want X to be 1987. And when I hit enter, it will calculate the CO2 Y value for me. They also said, what was it in 2005? They didn't collect data into 2005, so I'm using this as a predictor. If I hit second trace and I ask it to plug in 2005, it's going to give me an error message because it cannot calculate what it can't see. Right now, my window isn't going that far. So what I want to do is I want to zoom out just so that I can see a little more. When I hit zoom out the first time, nothing happens because it gives me the option to reposition this cursor right here. Wherever that cursor is when I hit enter the second time will be the center of my screen. So I really have to hit enter twice. So now I go back and ask it for 2005, and it has no trouble at all calculating that. Then they ask me, what year would it be when the CO2 levels exceed 400? So in this case, they're asking me what's X when Y is 400. I don't have a button for that. So how would I find that on my calculator? I could trace, but I'm going to need to like zoom in, trace, zoom in, trace, zoom in, trace. So you can see if I hit trace, now be careful because see right now it says P1, L1, L2. If I hit trace right now, all it's going to do is just trace along those boxes that I had plotted for my stat plot for list 1 and list 2. That's not going to do me any good. If I hit my down arrow, see now it switches to Y1, that regression that we had done, the equation there, that's what I want. So I'm going to trace, so I'm just going to move along here, and I'm looking for when my Y value exceeds 400. So I just trace, continue to move to the right. Okay, so I've got 3.99.9. That's probably pretty close, but look at my year, 2020.98. Oh man, I don't know if it would run over into 2021 when this runs over to 400. And if I use my arrow key one more time, now I'm too far. Now I'm past it. So that's why I would have to continually zoom in. So I could come over here to zoom and go to zoom in. And remember, before it zooms, it lets me position that cursor, which is really helpful because I want to get that as close to the 400 as I can on that line before I hit zoom in. So I'll hit enter again and it will zoom in from there. And I could trace, and again, notice when I hit trace, it went back to the plots again. I don't want that, so I'm going to use my down arrow key to get back to my equation. So now I'm at that 399.9. Now when I trace over, now I'm at 400.2. You can see I have a much closer approximations. So 399.9, I'm still not into 2021. and 400.25, I'm already past 2021. I still don't know when it happened. I'm going to have to keep repeating that process until I can get a clear picture where I'm getting the same year on both sides of that value. There is a much faster, easier way to do this. Can you think of a different way that we could do this instead of this whole zoom and trace thing? Okay, what if, since we want to know when this equation is equal to 400, what if we go back to y equals and we actually graph y equals 400? Now when I graph that, what am I looking for? Yes, where they intersect, exactly. So I'm looking for this point right here. So I could then use my intersect button on my calculator, number 5, and it's going to ask me, you can see it's positioned itself on what I have in y1. That was that regression equation. And now it's positioned itself on what I have in y2. That was that horizontal line we just put in. So enter for yes. So yes for the first curve, yes for the second curve. I think the point of intersection is about right here. So I'll hit enter and it'll verify for me that point of intersection was just barely into 2021. So now I have a clear answer to that question. So let's review what we did on the calculator today. All right, we went to to statistics, and that was edit. And then we went into edit to get into list 1 and list 2. It is good practice to scroll up to list 1 and hit clear enter. Don't hit delete. If you do, that whole list will disappear, like literally L1 will disappear. If by chance you do that, it's not tragic. You just come down here to setup editor and hit enter, and it will say done after you hit enter. When you go back, list 1 will be there again. Okay, so go up to list 1 and hit clear enter. It clears that whole list out for you so you can type the data in fresh. So we put our information from the table into list 1 and list 2. Then we went to second y equals, which was our stat plot. Turned the first plot on, told it to do a scatter plot, and told it to use list 1 and list 2. Now, if on the homework tonight you're doing a couple of these problems and you put your first set of information into list 1 and list 2 and you come to the next problem, you could always put that information into list 3 and list 4 if you wanted to. The only thing about that is when you go to do the regression, your calculator will automatically use what's in list 1 and list 2 for the regression unless you tell it otherwise. So I'll show you that in just a second. But we went in, told it to do list 1 and list 2. Then we let our calculator set the window for us. So we did zoom 9, which was zoom stat. And it created the window. And depending on what you told it down here, if you tell it to use little dots or you tell it to use blocks, here's where the graph is in dots, here's where the graph is in blocks. Okay, so here was that equation we had created. We typed it in and saw it wasn't really a great fit. We had a lot of these points that were falling below our equation. So we asked our calculator to come up with a better fit for that information. So we went back to statistics and we went over to calculate. We, because it looked linear, chose a linear regression, and it gave us A was 1.496 repeating, B was negative 2,624.826 repeating. So you literally could type that equation in where we put this in for A and this in for B. You could type that equation in on your own, or before you hit linear regression, you can tell your calculator where you want it to load it. Now, this is also where you would need to tell your calculator if you used lists other than 1 and 2. So you would say linear regression L3, comma, L4. And then it would do the regression of that information instead. All right? Wherever you tell your calculator to put this is where it will. So we said I had mine loaded into Y1, but we said you could have it loaded into Y2 or Y8 or whatever you want. So we did our shortcut menu to load that Y1 or Y2 or whatever value that you might want. Okay, so then we had a much better graph of that information, And then we were able to use that for example number 3 to apply some mathematics to it to answer the questions that were asked. So they asked me to estimate the average CO2 level for 1987. So we plugged in 1987 for X, and it gave us the Y value CO2 level. And easy way to do that, remember, is second trace, which is your calculate menu. Give it whatever X value you want. It'll generate the Y value. Similarly, we tried to do the same thing with 2005, but the first time you're going to get an error message because this window is not going all the way out to 2005. Remember that the last piece of information that we gave it was 1990. So if this is 1990 right here, it's really only going out to probably 92 or 93. If it can't see 2005, it can't calculate it. So all we did was just zoom out. So we went to zoom and chose out. Remember, you have to hit enter twice because the first time you hit enter, it gives you the option of recentering that cursor. The second time you hit enter, it actually zooms out. So then when I typed in the 2005, it had no trouble finding that value. The last thing that they asked me was to tell when the CO2 level would exceed 400 parts per million. So they're giving me a Y value and asking me to find X. I don't have a button for that. So we talked about 2 different ways you could do that. We said that you could either trace along your graph, and you would need to zoom in a few times before you could get a clear reading. So you could zoom in and trace, or what was much faster and more precise was to put 400 in Y2, and then when you had the graph, you were just looking for the intersection. And then it was very clear that it was 2021. Okay, so here is our homework for tonight on pages 36 and 37, just a couple of these because they're pretty time consuming. And you've got these screenshots of the things that we've done so that if you need to go back through step by step how we got to something, then you've got the pictures of how we did that.